Our research is on predicting purchasing decisions of online shoppers using machine learning. And this research was conducted by myself, Isabella, Shahab, Dorian, Philip, and T for the class IE4305 under the professor Dr. Lebulik. For this presentation, we'll start with an introduction, and then we'll go on to the methodology, the results, and end with a conclusion.
As we're all aware, global e-commerce sales have been skyrocketing since COVID-19, with a total of $4.28 trillion in revenue, which has a $2.95 trillion increase since 2014. E-commerce is expected to grow even higher in the future as people are turning to the internet for safe and convenient shopping options. As machine learning and artificial intelligence are presented across many industries, we think it will be beneficial to e-commerce businesses if a business can predict whether customers will make a purchase when visiting their website. Then they can analyze the information from the customers to better allocate resources and advertisements, and they can influence sales. We conducted this study using Python, specifically Pandas, NumPy, scikit-learn, and Seaborn libraries to analyze a large dataset. Using an online bookstore built on an OS commerce platform, the data was collected for research by Sochaki and Chodak in 2019. Our goal is to identify factors can be used to predict whether a customer will make a purchase when they visit an e-commerce site.
The data was collected over the span of 1 year, and each data point represents a different online shopping session. The response variable for this dataset is revenue, a Boolean variable representing whether the user made a purchase when they visited the online site. There are a total of 17 predictor variables that can be used to predict the response variable. 13 of these predictor variables are numerical, and 4 are categorical. There are 12,330 data points, where each data point represents a separate online session. Training a model with predictors that are highly correlated can negatively affect the scoring of the model when it is introduced to data in the test set. To ensure the model did not rely on highly correlated predictors, pairwise Pearson correlation coefficients were calculated. A confusion matrix was then used to visualize the multicollinearity. After evaluating the pairwise correlation values, 3 R values are greater than 0.7. All 3 pairs of predictors represent the number of a type of page visited and the total time spent on that type of page. So this correlation is expected. At this stage, no features will be removed.
So in this part, I'm going to talk about data pre-processing, and I'm going to start with encoding. Most machine learning algorithms require numerical values as input to interpret the data. However, the data collected in day-to-day business operations are not necessarily numerical and can be from different types. Different non-numerical data types include categorical, Boolean, and some examples are, as you can see on the screen here, for example, month of the year, February, March, May, or visitor type, returning visitor, new visitor, or even true false values like is it a weekend or not, or did we have revenue or not. When working with such variables, encoding is utilized to change the existing categorical variables to numerical variables. The dataset used for this project included 4 different features which required encoding prior to applying machine learning algorithm. In next stage, I want to talk about scaling as our next pre-processing step. When applying machine learning algorithms to a dataset, since most machine learning algorithms use Euclidean distance for their computation, it is preferred to provide features without extreme values or features with values similar to each other for better outcomes. However, in most cases, the data that's collected in real world have a wide variety of ranges, and it's not suitable for direct use by machine learning algorithms. And in order to ensure that all features have equal contribution, we apply scaling to remove the effect of varying ranges. For example, in our data, our range values varied from 0.2 all the way up to 63,973.52, as you can see in the table over here. So we applied the scaling algorithm, which basically changed all the range values between 0 and 1. So all values are now placed between 0 and 1, and we're not going to have any bias when applying our machine learning algorithm. Next step in our pre-processing was a smooth or synthetic minority oversampling technique. So after separating our data into testing and training sets, it was clear to us that the training data set was an imbalanced data set. This type of training data can result in a model which is biased toward one value rather than the other one. And in our case, as you can see, it could be biased towards zeros other than ones. And the reason is, as you can see, we have 84.5% of samples labeled as 0, which means no revenue or there was no purchase by the customer. And then labeled 1 was 15.5% of the samples, which is our positive class, or that means we did have revenue. And so in order to accommodate for this issue, a SMOT was applied to the training dataset. A SMOT is a method which will increase the number of samples in the minority class without adding any samples to the majority class. And it will return a dataset containing the original dataset with the additional points added. And this method will ensure that the training dataset is balanced and the model is trained with unbiased dataset. And you can see here in the picture at the bottom right that after applying a SMOT, our data set was balanced and number of samples for zeros and ones are equal.
So here in the preliminary models, when testing these models, we had to use each one based off the F1 score and accuracy to determine which machine learning algorithm would give us the best data. We had tested 6 different models, and each model with 4 different scalars. The models used were random forest, support vector machine, logistic regression, k-nearest neighbors, decision tree, and Bernoulli knife Bayes. The scalar each model was tested on was standard scalar, min-max scalar, max-ab scalar, and normalizer. With the goal to have the highest accuracy and F1 score as possible, we narrowed down to the best 3 machine learning algorithm models. So in the preliminary model selection, as you can see on the graph, the 3 best models were random forest, support vector machine, and logistic regression. With the top models being in the top right, you can see as to why these models were selected. The first selected model, random forest, uses the outputs from several decision trees to make a prediction with its parameter tune being the n estimators. The second selected model, support vector machine, is used to find a hyperplane, which is an n-dimensional space that distinctly classifies the data points with its parameter tune being C. The third selected model, logistic regression, which is a predictive analysis algorithm based on probability and uses a complex cost function defined as the sigmoid function or the logistic function, its parameter to tune also being C.
Pre-processing was revisited to ensure that we were able to have a standardized approach for all selected models. The following pre-processing method was applied to the dataset after the categorical variables were encoded, and the resulting pre-processed dataset was used as input when generating the models and tuning their parameters. First, the predictor values were set to a range of 0 to 1 using a min-max scalar for all 3 models. This is because of the different scalars applied during the model selection process, random forest performed best using the min-max scalar. Although logistic regression and SVM perform best using a normalizer, when tuning the selected models, we wanted to apply the same pre-processing across all models. Second, the dataset was split into a training and test set. The training set contained 70% of the data points, and the test set contained 30%. The training set was solely used to evaluate model performance. Also, the same training and test sets were used for each model. And finally, SMOT was applied to the training set for each model. No synthetic points generated from SMOT were added to the test set. This way, the risk of potentially biasing the test set with synthetic data is mitigated. To improve the three best preliminary models, the GridSearch CV parameter approach was used. GridSearch CV is a tool provided by the scikit-learn Python library. With GridSearch CV, one can search over a set of user-defined parameter values and use cross-validation to choose the values that will most improve the model's performance. To apply GridSearch CV, we grid searched 5 different parameter values for each of the 3 best preliminary models and cross-validated them using a stratified k-fold cross-validator with k equal to 10. So why use cross-validation for parameter tuning? Well, the purpose of cross-validation is to evaluate model performance on the data that the model hasn't seen yet, and it can shed light on problems such as overfitting. How was cross-validation used? A stratified k-folds cross-validator split the training dataset into 10 subsets or folds and maintained the training data's class proportions in each subset. Since SMOTE was applied to the training data prior to using the stratified k-folds cross-validator, the classes in each subset were balanced with 50 samples labeled as 0 or no revenue and 50% of the samples labeled as 1 or revenue. After splitting the training data into 10 subsets, the model was trained using 9 of the subsets and tested using whichever of the subsets was left out. This process was repeated for 10 iterations, leaving out a different one of the 10 subsets each time.
So here are the results, and we have these 3 different selected models. For the first model, random forest, so out of all the random forest models grid search, the best performing model had the parameter of n estimator set to 300, meaning there were 300 decision trees in the model. 300 was the largest n estimator's parameter value grid search, and it makes sense as to lead the best performing model, since increasing the number of decision trees usually improves model performance. Although increasing the number of decision trees comes with an added computational expense, the trade-off is worth making in this case because the parameter value is still small enough that the model training time is not an issue. Additionally, SMOTE helped ameliorate the effects of the class imbalance, but the precision and recall scores for the no revenue class are still considerably higher than the scores for the revenue class. For support vector machine results, the best performing SVM model had a value of 100 for the C parameter. C is the regularization parameter for SVM. As the value of C increases, the strength of the regularization decreases. Since the default value of C is 1, this means that the SVM model is performed better with the regularization strength weaker than the default. Of the 3 selected preliminary models, SVM had the lowest precision. This means that SVM classified more samples as revenue when the sample was actually labeled as no revenue. For the logistic regression results of the C parameter values grid search for logistic regression, a C value of 1 is yielded the best performing logistic regression model. Since the default C parameter value is 1, this means the default regularization strength worked best for the logistic regression model. The best logistic regression model had a lower mean test score than the SVM and random forest. However, the logistic regression model's mean test score had a smaller standard deviation than the random forest and SVM. This means that although the logistic regression has the lowest accuracy, the accuracy value has more consistent across the 10 cross-validated logistic regression models.
After using GridSearch CV to tune the parameters for the random forest, SVM, and logistic regression models, these 3 models were each evaluated for their overall accuracy and F1 scores. The training set with SMOTE applied was used to train the final models, and the test set with no SMOTE applied was used to evaluate model performance. Random forest has the highest accuracy and F1 scores, and random forest and SVM both had slight improvements in their accuracy and F1 scores, whereas logistic regression saw no improvement. This makes sense since the best C parameter value found through grid search for logistic regression was the default parameter value of 1, so no parameter value is changed from the default for the final logistic regression model. The ROC curve shows the true positive rate versus the false positive rate across possible classification thresholds. The true positive rate is also known as sensitivity or probability of detection, and the false positive rate is also known as specificity or probability of false alarm. Increasing the classification threshold increases both probability of detection and probability of false alarm. With some applications, it is more important for the model to identify all true positives, and in others, we must classify all true negatives. The ROC curve can help identify the best model for a certain application. For a classification threshold and variant metric with which to compare the models, one can take the area under the ROC curve, and the highest valued model generally perform the best. The random forest model is represented by the blue curve here, and it had higher sensitivity and specificity than the other models across all classification thresholds. This model has a higher area under the curve than the logistic regression and SVM algorithms.
In conclusion, random forest was the best selected model with an accuracy of 88.8%. This score means there's 88.8% chance random forest model can predict whether an online shopper will make a purchase when visiting an online bookstore, which is a very high percentage for retail business. Thus, e-commerce companies can analyze data using machine learning to better allocate resources in advertisement. Further research can focus on finding the features that best predict the response variable. E-commerce businesses can use these features to improve their advertising strategies and resource allocation. And thank you all for listening. And we also would like to thank Dr. Lebulik for helping this research.